Let's continue the story of trying to make numbers as sums of squares. Or we looked at, I briefly mentioned x squared plus 5y squared, and that is relationship to some other videos. Here's the generalization of 3 squares that you could put in coefficients. Can I make any n as 2x squared plus 3y squared plus 7z squared? Okay. That one, it's actually pretty easy to see that you can't. But we'll come back to the idea of putting in coefficients in a minute when we kind of get to the general problem. Still kind of working up through classic examples. So now we're up to a famous result of Lagrange, the Foursquare theorem. You might think it's a little weird that this is earlier than the Legendre result. The Lagrange result said you can make anything out of 4 squares. So finally we got something that really works for any positive integer. And then people went back and said, well, what if you only gave yourself 3? And it's actually a sort of a more subtle question to figure out that you can't get those things that were of the form power of 4 times something that's congruent to 7 mod 8. So here's the kind of, one of the very natural stopping points in our story. This is the first form, this is the first kind of algebraic expression called a quadratic form on the right that you would call universal, that it represents any positive integer n. I'd say that it's not too shocking if you knew the 3-variable result already, which is not historically how it went. That's not a very thick set of numbers. Things that are, there's only that one 7 mod 8 that was the real problem, and then the 4s were kind of another problem. And so it's not too shocking to give yourself one more degree of freedom. You can create every number. But it was a big deal. And I don't think this can't be the original. Yeah, this is not even close to the original proof, but the classic proof you'll see nowadays is the 2 squares result. If you watch the -163 videos or know anything, watch anything or look at anything about the Gaussian integers, famous thing about the Gaussian integers, which is the analog of the integers in the complex numbers, it uses the theory of factorization and primes in that algebraic structure, what's called a ring. Well, it turns out that to do the Foursquare proof, you look at the quaternions, which is where you add not just I, but j and k to the real numbers. That produces a 4-dimensional algebra, which has some wonderful uses. And it turns out that the analog of the Gaussian integers are called the Hurwitz Integers. There's some slight complications with 1/2 and things like that. And you can make a proof that's analogous to the 2-square proof. So it's a beautiful story. Not where I'm going with these videos. I probably will make a video about that at some point. So here's another thing you could do. I've been mentioning this briefly already. You could also look at, this is really a perfectly legal quadratic form. Even though it's not just a sum of squares, it's something where each term has the same kind of weight. They're really the same. They're degree 2 in terms of algebraic terminology. That's degree 2 because it's x squared. That's degree 2. This is degree 2 because it's a degree 1 times a degree 1. For example, one way you can tell something is really deserves to be called quadratic, even if it has 2 variables, is you just double both of the inputs and you see what happens to the output. It does go up by a factor of 4, which is exactly the same thing that x squared and y squared would do. So this is called a completely legal quadratic form. It's just not something that's it's something that has mixed or cross terms in it. So that's legal. So here I finally get to the general form. So we've got, let's imagine we have k different variables, x1 through xk, and we create a function that's of this form. So this looks a little bit hairy, but you can look at the example if you want. It's just some number, and a good way to label that is a11, times x1 squared, plus some other number times the product of the first 2 variables, plus some other number times the product of the first and the third, all the way to some coefficient in front of the square of the last variable. So it's all the things where you have numbers like this example here, 7 times u squared, another number times uv, uw. It's anything where you take the product of any 2 of them and then you square any one and you put integer positive integer coefficients in front. Well, they don't have to be positive really. If you flipped one of these signs, like if you flipped maybe this one to a minus sign or something, although I'd have to check, it's not easy to do by inspection. You can flip some of those signs and still have it be positive definite. That is, you can't actually get a negative number out of it if you put in positive inputs. So here's the question. Can every positive integer n be represented in that way? You fix the number of variables and you fix the coefficients, And then you ask, what are the outputs of this thing? It's going to be a bunch of integers. Is it all possible integers? Can I be in some clever enough combination of u, v, w, x, and y, and z, can I get any positive integer out of this? And if that's true, we call that form universal. All right, so it's a matter of determining universal quadratic forms. Well, I'm not actually going to tell you some way to specifically, some beautiful answer to that question. I'm going to tell you something about the answer to that question. The answer is sometimes yes and sometimes no. It turns out to be very important in lots of far-flung fields, like from number theory all the way to topology, to figure out that question. There's a lot of deep stuff to it, and the answer is complicated. There's still, I think, stuff that's really unknown about it. One thing that's true, which you might have guessed from the examples that I showed you, is that if you use less than 4 variables, then you can't ever get all possible numbers. So all these examples beforehand, like this one, or just the sum of 3 squares, none of those could have been universal. And that's a generalization of the story around Lagrangia's Foursquare theorem. It says that really, yes, you can get everything from a sum of 4 squares, but you can't get anything from a simpler prescription with squares. Okay, so here's something that I've been trying to lead up to, whenever I've been looking at these forms and talking about where the first counterexample is. Suppose you have a non-universal form, something where the answer is no, you can't create every integer. Is it possible to get a long string of misleading yes answers? So could you have a non-universal form that maybe with 17 variables or something, and it seems like it's going to create every integer. It creates 1, 2, 3, 4, 5, 6, 7, all the way up to some ridiculously huge number. Okay, maybe 10 to the 300th, or even a billion would be kind of frustrating, because it would say that you can be misled by this very easily. Well, here's the big theorem. The answer is no. That it turns out that if you can't represent every number, I guess do isn't a very specific word. If you can't represent every number, then a counterexample will actually show up quite soon if you start from 1. And quite soon really is I mean, we're talking about a really small number. There's going to be 2 versions of it pretty soon. But it's a pretty amazing fact that you just have to check a small number of n's, and then you can guarantee that that form is going to be universal. So there's some magic number n, and the reason I'm not putting it in as a specific number here is that there's 2 versions, as I said. And if you check up through that magic number, then you're done. Okay. So why am I being coy about what the magic number is? It's because there's a little bit of an annoying inconsistency about what we really mean by an integer quadratic form that I haven't told you yet. So it depends on which formulation you pick. And the really nice simple answer, unfortunately, requires a restriction that's not very pleasant. So Conway and Schneeberger from 1993, they looked at a smaller class of integral quadratic forms. They looked at special ones, those with what's called an integer matrix, and I'm going to tell you what that means in a minute. And then they conjectured what would happen if you didn't have the restriction, and then Bargava and Hanke in 2005, pretty recently, removed that restriction, but you need to search further to be sure you actually have a universal form. So let me talk about that. What the heck does an integer matrix mean? So one way, so you have to know a tiny bit about matrix multiplication for this part. One way to get a very, very natural way to get a quadratic form is to start with a symmetric matrix. Okay, so I'm going to start out with, let's look at the expression x squared plus 4xy plus 2y squared. Turns out that anything of that form you can get by taking xy as a row vector on one side and xy as a column vector, and put a symmetric matrix in between. Symmetric means symmetric across the main diagonal, which goes down here. So this is equal to this means it's a symmetric matrix for a 2 by 2 matrix. Another way to say that, if you know about transposes, is the matrix is equal to its transpose. So matrix multiplication says, well, let's see, I've got 2 matrix multiplications to do, the one in between here and the one in between here. So let's do this one first. It's you take this row and you pair it up with this column. So 1 times x plus 2 times y. There we go. 2 times x plus 2 times y. Or plus, that should be a 2. And that should be 2, and that makes sense. Okay. And then, again, you do another matrix multiplication. Row times column, okay. X pairs with this, plus y pairing with this. So it's x times x plus 2y, and then y times 2x plus 2y. You simplify that out, and you get, indeed, x squared plus 4xy plus 2y squared. Another example would be with 3 variables. This big, nasty quadratic form, I claim it comes from this matrix. If you take 5, 3, 7, 3, 3, 1, 7, 1, 1, you can verify that it gets you 5x plus 3y plus 7z. Notice those are just the same numbers turned into coefficients. The 3, 3, 1 turn into coefficients here. The 7, 1, 1 turn into coefficients here. And then if you pair these together, you get, for example, 5x squared plus 3xy. Well, wait, I'm not getting 6xy. Ah, that's because you're also going to get a y here times a 3x. That's going to give you another place with 3xy. They combine to be a 6xy. So this is very important. We've got two things combining to be this 6, so that's going to be even. For example, here you might have wondered, this is a 4. Why are these 2's? Oh, it's because it's coming in two places. X times 2y and y times 2x both contribute to be part of the 4xy. Okay? So this cross term and this cross term and this cross term had to be even to be able to write it this way and still have this matrix be integers. Okay? So that's what I've got down here. The cross-term coefficients must be even if it's coming from an integer matrix. Now, there's nothing that says you can't write this in terms of matrix arithmetic. Even this one, x squared plus xy plus y squared. It's the simplest one where this one is not even. It's not very hard to verify that it comes from this symmetric matrix. Okay? But pretty clearly that is not an integer matrix, not a matrix with integer coefficients. Okay? So this is the distinction, that this guy is perfectly legal if you require your form just to have integer coefficients, but it's not legal if you want the matrix it comes from. If you think of it as coming from a matrix and you want that matrix to have integer coefficients. Okay? So really it's just saying the cross-term coefficients have to be even. That seems kind of finicky, and unfortunately we've got two things you can say about it. One is that, well, like 100 years ago or 200 years ago, it was really not clear which rule you'd want, and I think from my minor knowledge of the history, most people would have allowed this or would have not allowed this, sorry, in the, maybe 200 years ago. They would have not liked that because it doesn't come from an integer matrix. The modern view is that it's an unwanted restriction and you want to be able to deal with these kinds of examples. But matrix algebra, linear algebra, wow, that's powerful stuff. And it'd be nice to be able to do this, and if you have to put the 1/2 in here, it turns out to be much, much harder. Okay, so that's why the Conway-Schneeberger result, they first looked at the integer matrix case because they knew it would be easier. And what they discovered is the magic number in that case is 15. Very nice, small number. So what that says is you've got some algebraic expression, one of these quadratic forms with integer coefficients, and the cross terms are all even. Here, I happen to have 0 cross terms. Okay, so of course they're even. And the claim is that if you check that it represents all the numbers 1 through 15, then magically you can be sure that it will represent every other number. That's really cool. That's a very effective result, a way to take what could have been an incredibly hard thing to determine and make it into a very finite calculation. So, for example, this form is designed to show that you actually have to check through 15. This guy represents all the numbers. If you look at the list, and I didn't do it all for you, but you can check. It's kind of a fun little calculation. You can verify that you can get everything 1 through 14 with this guy, but nope, 15 is impossible. Okay. To show that it's impossible, it's pretty easy to show that you have to have the y and z, the ones with the 5 coefficients. They've got to be either 0, 0, 0, 1, or 1, 1, and then for each of those, it's easy to check the possible cases for w and x. Just basically sort of intelligent case checking, and you can show that it's impossible. So then I'm going to say a little more in the last video about refinements to this result, and then what the 290 comes in. Although you can guess probably why the 290 comes in. But it's just, this is a very simple, nice way to say it. As long as you have that integer matrix restriction, you just get this really small finite list of numbers you have to check, and boom, you can just conclude it's universal. Of course, it's a very hard and tricky theorem to prove it, but I'm not interested in the proof right here.